to share this 12th session of MRAM Forum. So this event usually takes place as a spin-off of IETM conference, but it was cancelled last Christmas due to the well-known complex COVID situation. Instead, it was decided to shift it during this INTERMAG event, giving opportunity to microelectronic people to discover even more on emerging magnetic phenomena. I take opportunity here to announce that the 13th edition will again happen in next IETM event next December. In person or virtual, that we don't know yet, but only one way. So let's hope that it will be in person. As you may know, MRAM Forum was initially created to bring closer the microelectronic and magnetism communities. We can say that nowadays this has been paying as major microelectronic industry and tool suppliers are really active in this area. And actually, foundries are now launching volume production of STT-MRAM, which constitutes a major achievement for spintronics community, with exciting openings for spintronic emerging concepts and applications. Okay, so now shifting to today's event. We have a Q&A session of 10 invited speakers, coming from academics, R&D, and industrial worlds. I remind that all of these talks will be available until end of June. As you may know, we had to deal with complex time zone game, with audience and speakers from Europe, US, and Asia. So let me acknowledge the speakers. I know that for some of them it will be a hard time, as for example, it is actually middle of the night in Europe. I would also like to warmly thank all the speakers for their high quality presentation, which is meeting our initial expectation when we built this program with Luc and Bernard. We wanted to give the attendee a broad overview of requirement to ramp up a technology from lab initial discoveries to fab environment and constraints, and to explain what are the challenges to bring this technology to a market reality. For this, we will have presentation about material and process integration challenges, about MRAM product development, but also very importantly about design to technology interaction and system level considerations. This session will be closed by some perspective on beyond standard STT technology, SOT, VCMA, 3D integration, AI, and probabilistic computing. A lot of exciting topics that may become one day a reality. So now let me remind you that this MRAM session forum Q&A session will be followed by a panel discussion about this important topic. What do we need to bring MRAM to next level? And finally, before closing these opening remarks and starting with our first presenter, here is how should take place the organization of the Q&A session. Before each speaker turn, we will have a 3-minute video recap of their presentation. After this, the speaker will be on stage for 5 minutes to answer the questions of audience. I invite you to pose the questions in the chat box, and I will rephrase them to the speakers. If possible, state your name and affiliation. So now, before starting, let me precise that there will be a slight shift in the order of the program, and we will start with a first presentation given by Sahil Patel from Applied Materials.
Hi, my name is Sahil Patel. I work for Applied Materials, and today I'm going to give a quick summary of my talk titled Engineering New Processes for the Enablement of Advanced Node Embedded MRAM. So my talk today focuses on process technologies that are developed at Applied Materials on Applied Materials tools, where we're focusing at improving the MTJ performance for MRAM devices at small CDs. And the big message I want to get across in the talk today is that we're trying to focus for these small CD devices for advanced node MRAM on combining the MTJ stack PVD etch process and encapsulation process, and trying to co-optimize these 3 factors that go into depositing and then also patterning the MTJ bit to get the final device performance to improve and to be able to be compatible with advanced node transistors. So at larger CDs, we typically work on improving the MTJ film stack and use whatever etch and encapsulation processes available from the semiconductor industry. And here I want to describe some improvements from the etch and encapsulation process together. So the big takeaway from this presentation and this paper is that we can run a few different processes. So in the paper, I'll talk about 5 different processes for etch and encapsulation optimization only. And the big thing we can do is look at the size dependence of three parameters: the TMR, the switching voltage, and coercivity. And we can see that these processes have very different effects on key parameters for the device performance optimization. So looking at these five processes, we can see that we have a really big switching voltage reduction from this process number 5, which is a combination of learnings we have from these first 4 processes. While we don't have too much of a TMR drop, we can still have a fairly high device TMR compared to the film. And we also have very high HC. So I will go over some of the details of the improvements we made in these processes today. And finally, what the final outcome of this work is that we can see that for looking, when we project out and look at the deep error rate down to 1 ppm writing current, we can see that we can meet or get close to what's necessary for advanced node MRAM compatibility in terms of 1 ppm write currents, while still having good performance for the other MTJ parameters. So I show here that a 28 nanometer ECD, we can get down to about 77 microamps, and we think that we can improve this with further patterning improvements so we have better CD non-uniformity. I hope you enjoy my talk, and I want to thank the conference organizers for inviting me here to give this talk. Thanks very much.
Okay, thank you very much, Sahil. So let's see if we have some question in the Q&A. Not yet. So I will start with one question which was posted actually on the presentation. So from Alvaro Palomino from SpinTech is asking you if you can remind in slide 17, you show that IC is reduced in film A compared to film B, and having both followed by same optimal encapsulation and edge condition. Do you believe this is due to improved crystallinity of the MGO barrier alone, or can come from different free layer thicknesses? As you mentioned, you improved both processes in slide 16.
Sure. Let me quickly look back at the slide. Yeah, I think, we do think that there's an improvement of MGO crystallinity at the edge of the device, and I think that's what really contributes to the improvement in terms of JC, and that's why we see this IC reduction. There is some improvement in terms of the film and film properties to get us there, but the big thing that we're trying to show is that it's not just the film that it reduces the write current. It's improving the etch and encapsulation. We can actually improve the crystallinity at the edge of the MTJ, and therefore get a better spin transfer torque even at the edge of the MTJ, and therefore reduce write current.
And does it result also in an improvement of TMR?
Yeah, I think we would expect it resulting in improvement of TMR, and sometimes in some cases we do see that we have an improvement of TMR or the same TMR for a process that can reduce writing current. In this case, we do have a little bit of a reduction in TMR. So we would expect to have this high TMR from this higher spin polarization at the edge of the device. And that's something that we're still researching, still trying to investigate to understand what's going on.
Okay, thank you. So now I have a question from Feng Zhao. What can dominate the cell size? Is it the CMOS transistor size or the MRAM stack size at 28 nanometer node?
So I don't think it's the MRAM bit size of the 28 nanometer node. I mean, this is based on the CMOS transistor size, not just the transistor size, but the footprint of the circuit. And so in this case, at 28 nanometer, I would say it's a CMOS limitation, not an actual MRAM bit limitation.
Okay, so now I have some market opportunities for you. So there is Mark Keefe from Seagate, I think, that is asking if the module of a ribbon etch is available for 200 millimeter format.
I think, yeah, so right now that's not available for 200 millimeter, I can say that. Sorry about that.
So I had actually another question. So you are showing in your presentation, so basically most of the things you plot with 2 different CDs, and you are not showing trends with more CDs. What are your restrictions for this? Is it the
Yes.
mask set design or?
That's right. So I think right now it's the mask set design. We have on our mask design, we have 2 CDs that can yield. Obviously, if we had more CDs, we could understand a little bit more and fill in the space in between. But I think one thing that we do have is this mask set design, which allows us to measure a kilobit devices per die, which is pretty useful in looking at distributions, and also looking at short rate in terms of PPK level defectivity. So we do like this design, and we think by using 2 CDs, we can at least get some ballpark understanding of what the size dependence is.
Okay, so now a question from Gis Shimon. How much is the damage proportion in a ballpark, at least, coming from the etch damage versus NCAPS damage?
This is a good question. I think these 2 processes go together. I mean, they're obviously occurring one right after another. I mentioned in the presentation that these are in situ deposited encapsulations. So we have them all in the same high vacuum mainframe. So the way I like to view it is to view it as the same processes working together. So I think these 2 etch encapsulation process, it's hard to decouple what would be etch damage and what would be encapsulation damage because they happen at the same time. We can't really decouple them very well.
And I assume you have been trying different type of NCAPS to test the impact on damage.
Sure, and we do try different types of encapsulation, but again, it's a combination effect. So if we have a different etch, the dependence on encapsulation is going to be different. And so we have to look at them together to get the optimum. And we can't draw out which one is etch damage and which one's encapsulation damage just by itself, I think.
Okay, so I think we can stop the questions here. Thanks a lot for your presentation. It was very nice work and very good progress for tool development. And looking
Thanks very
forward
much,
your
Kevin.
next
Yeah.
work.
Thank you.
And so now I propose that we move to the next speaker. So next speaker will be Tiffany Santos from Western Digital.
Hi, I'm Tiffany Santos. I'm part of the non-volatile memory research team of Western Digital in San Jose. I'd like to thank the organizers of the MRAM Global Innovation Forum for inviting me to share this work here today. So the goal of this study was to reduce the switching current for the free layer in a magnetic tunnel junction while maintaining a high thermal stability factor for data retention. The way that we went about doing this was to lower the free layer thickness, but keeping the saturation magnetization high and the damping constant low. This is our free layer design here. It is a cobalt iron boron based free layer with an MgO tunnel barrier at the bottom here and an MgO layer as a cap. We have this tungsten layer inserted into the free layer. This tungsten layer is known to reduce the MS of the cobalt iron boron. So we want to minimize it as much as possible, here down to 0.4 angstroms in thickness. This has enabled us to reduce the total free layer thickness to 13 angstroms. We found that we can improve the magnetic properties even further by splitting this tungsten spacer into 2 even thinner layers here while keeping the total free layer thickness the same. We proceeded to do this for a free layer thickness ladder, 12, 13, and 17 angstroms. And for each thickness, we have 2 free layer designs, one with a single tungsten spacer and another with this split tungsten spacer design. We see here that the MS is highest for the thinnest free layers that have the least amount of tungsten. And we've maintained a very low damping constant down to 0.003, even for the thinnest free layers. So we proceeded to study these 6 free layer designs in bottom pinned MRAM stacks with electrical CD in the range of 55 to 130 nanometers. And these are the results here. This is the thermal stability factor. It remains quite high, even for the thinnest free layers. In the center, I'm showing the critical switching current density. It is highest for the thickest free layers. And we have a reduction by 30% for the thinnest free layers that have the 2 tungsten spacer design. So that overall, the spin transfer torque efficiency is highest for these thinnest free layers that have the 2 tungsten spacers. So you can find more details of this work in this recent publication or in the longer version of this talk. Thank you.
Hi, Tiffany. Thank you very
Hi.
much for your presentation. So, not yet some questions. They will come with time. So I was wondering if you tested, so the delta values that you are reporting for your stacks are very large. And how does your delta extraction compares with macrospin modeling?
So they're large, but it's also at a higher CD, 55 nanometer and above. So really, because we're above 20 to 30 nanometers, the macrospin model does not apply here, and we use the domain wall reversal model.
Okay, so you think that the reversal is not macrospin at these dimensions of 50 nanometers, with because in my understanding, with the large entropy values that you have, we should be more in the macrospin regime than in domain wall regime, isn't it?
Yeah, not quite. So these free layers, they do give a high exchange constant. So the domain size is large. However, still at 55 nanometer, we're still in the domain wall reversal regime.
Okay. I'm waiting for some questions to come.
Sure.
But they are not. So did you test your stacks or your devices versus temperature? And do you see a strong impact of temperature on performances and retention?
In this particular experiment, we did not extend to higher temperature studies. But just in general, when we go to higher temperature, for example, sometimes we're interested in looking at what happens at thermal stability at 100 degrees C. We do see that reduction in thermal stability due to expected reduction in HK for the free layers as you go up in temperature.
Okay. So there are some questions from the Q&A of your longer talk version.
Mm-hmm.
One, so you answered most of them.
Yeah. Yeah, it's good to see a lot of questions posted there. So thanks, and I encourage people to use that.
And yeah, I guess you will continue answering. So most of them are related to the stack performances. And let me just rephrase one of them. Okay. So I have a question from Noel Abara. What thickness precision do you need to get the properties over an entire wafer, especially with tungsten dusting?
Yeah, so that's a good question, and it comes up, I think, because we're using very thin layers of tungsten. But we do try to ensure uniformity across the wafer. We reduce the power for the sputtering, and then we have, of course, the wafer is rotating. So we are able to get within wafer uniformity of these properties and also wafer to wafer. However, because some of the thicknesses are so thin, it is very sensitive to thickness, so we always have to keep an eye on checking for that uniformity and any drift of sputter rates over time.
And do you see signatures of non-uniformity of deposition with statistical data, or
no, not in this study.
Okay.
Yeah, but for this study, the data is collected for 40, 50 devices per size.
Okay. So one more tricky question for you. What is the main goal of the MRAM application in the Western Digital? Is it for buffer memory or something else?
Well, I'll just say that we are interested in storage class memory and exploring that area. Yeah. Just trying to get some push the performance of the MRAM at small device sizes.
Okay. So when you say storage class memory, it means that you're also targeting quite high density. So you are relying on other tool suppliers for managing the edge capabilities, I guess.
Yeah. We're exploring if that's possible, and we're interested in being able to etch at small sizes and higher density.
And what would be the typical CD target that you would have?
I'm not gonna say
No,
anymore.
Okay. So thanks a lot for answering all these questions. And I think now we can move to next speaker. So maybe you want to say goodbye or too late. So thanks a lot.
Thank you.
And so next speaker will be Eric Edwards from IBM.
Hi, my name is Eric Edwards, and welcome to the summary of my talk on the development of high-performance MRAM and related technology trade-offs. In this summary, I'll go quickly through some slides that are covered in more detail in the extended version of the talk. Now, while you might target MRAM for several different applications, the application of interest to us is using embedded MRAM to replace SRAM in the last level cache application. The key requirement here is, among others, is a very fast read or write speed of around 2 to 3 nanoseconds. Now, when targeting such fast read and write speeds, in particular fast write speeds, we're faced with the major technological challenge that as we increase the write speed or decrease the write pulse width, the write current and the write voltage of the magnetic tunnel junction cell diverges large. And this is substantial below 100 or 50 nanoseconds, depending on the stack. At the same time, if we want to yield large functional MRAM chips, we must concern ourselves not only with the right voltage, but also with the right voltage distribution. All other things being equal, these trade off approximately 1-to-1, as I've shown here, as a pictorial result of the yield model. And in order to increase our margin and relax the requirements as much as possible on the right voltage, we must decrease the right voltage distribution as much as possible. The recent results we've been able to obtain, which are very promising, is that we've been able to realize a significant improvement in the right voltage distribution at fixed resistance distribution in our magnetic tunnel junction cells at these fast write speeds. That's depicted here on the right graph in terms of a stack comparison of stack 1 to stack 2, where the improvement is on the order of 2 to 3 percentage points at fixed resistance distribution across a wide range of resistances. And that's substantial in terms of the practicality of realizing ultra-fast write speed magnetic tunnel junction arrays. Particularly interesting is that in the optimized stack, the write voltage distribution is approximately independent of the write pulse duration down to the measuring limit of 2 nanoseconds. And here, at 40 nanometers, the value of the write voltage distribution is on the order of 4 to 5%. Another very nice result is that over the full array at 3 nanoseconds measured to a depth of 1 ppm or 0.3 ppm, we find anomaly free write performance in terms of write error rate scaling. And this is again very promising for the development of large high write speed MRAM chips. Here's the summary for the full talk. Overall, the demonstration of this kind of distribution and write performance at 3 nanoseconds across our several kilobit research test vehicles demonstrates for us an excellent basis for the development of last level cache type application MRAM chips in the near future.
Hello, my name is John Park from Samsung Electronics.
Hi, Eric. Thanks for your talk. So basically, in your presentation, you are mentioning that your stacks have a great potential for last level cache and even a bit higher in the hierarchy. So, as the status of today, what do you think is missing to really bring your stacks into this type of applications?
So I think there's Oh, yeah, one thing I would say that relates to some of the foregoing talks is there's a lot of work, on the integration side that you need to accomplish to take it from a research test vehicle like we have here to a tight pitch, current constrained advanced node. In terms of the right characteristics themselves, I think we're on a good path there, but that has to come together with very high endurance and these kinds of things, which you need to optimize once you've hit your product chip. So I think integrating what we have from research into a real test site or product, and then optimizing the full picture is definitely work yet to be done. But on the way there, I think what's really promising to us so far is seeing these 1 transistor, 1 magnetic tunnel junction cells perform at all in the range of 2 to 3 nanoseconds, which is pretty challenging.
Yeah, and actually, one question related to this is so basically, so far you are testing 1 kilobit array, if I remember correctly from your presentation. So do you think that, yeah? So do you think now if you are going to enlarge your array with more lines, that this will impact your writing speed or writing latency rather than the speed of switching?
It's a great question. Of course, this will play a role. Let me highlight for you what I think is most significant that we can test to the depth of this, 1/4 kilobit, let's say. And that's these pictures that we put up on, measuring the full array or all the yielding bits and not finding any anomalies. So this is I think it's kind of in the literature, and it's known, you can find some good devices, that perform very well, maybe some hero devices, but finding this kind of performance, at least to the depth we're able to test, that for us was very nice result. And yeah, we'll see. We'll put it in a bigger chip and find out.
No, that's actually indeed a very nice result. So here we have a question from King Yao Chiang. So he's asking, if we increase the I/O, then the write power will increase a lot. What is the trade-off here?
Okay, I/O.
So I guess this is a VDD. Yeah.
This is I'm not sure the end point of the question, but yeah, if you're developing MRAM for cache, this is everything, right? In other words, your application profile is very active read and write. And so every millivolt or microamp is critical. And when you're on the part of the write speed scaling curve that's diverging, this is why we work so hard on the distributions, right? Somehow you have to get every bit of margin you can for the right performance. So this is the trade-off. It's very important from the right performance perspective.
Okay, and then a question from G. Shimon. Do we have the same conclusion looking at absolute VC sigma instead of VC percentage sigma? So I guess this relates to your 2 graphs and ways of plotting.
Generally speaking, the answer is yes. I mean, you will see on the plot, I think even showing the summary, where we look at like write voltage in relative terms versus the pulse width. It's actually going down a little bit when you go to short pulse width. So it is growing slightly, but in fact, this is kind of a very favorable scaling, even if you plotted an absolute VC sigma. So what is absolutely not happening is that at very short pulse widths, you have some explosion or rapid growth in the absolute VC sigma.
Okay. And so one question about the stack failures, basically. So do you see any write balloon? And I would also mention there is ballooning and backhopping phenomena. And
this is kind of one of the key parts of these results is basically in these optimized stacks we don't, right? We see a lot if you develop 4 different parts of the parameter space, of course, and as you mentioned, backhopping as well. That's for sure, I think, something that is critical, and of course, if you go into very small sizes, it can be especially challenging. So I would say in general, we do see it, but kind of one of the key selling points of interest in what we found here is that these optimized stacks for distributions, they seem to have no ballooning to the depth we can detect in our research arrays, right? So.
Mm-hmm. And this ballooning actually is coming from free layer imperfections or material defects, or is it coming from processing? Is it something that you can say?
Yeah, I don't think we're going to say for like a wet stack or where we are. I mean, like too much detail there, but yeah, I would say we see many different varieties when you're trying to optimize this, right? You asked in the last, or someone asked in the last talk, what size? I mean, from one perspective, for the cache as small as possible, you can get as much current gain from shrinking your size. But that has limits on the damage you do to the device and this kind of ballooning poor performance you can find. So we see it, but when we optimize and the results shown here, we actually find it nowhere on the full 4 kilobit array.
Okay, so thanks a lot. We are going to stop the question here. And so next talk will be given by or presented by Young Hoon Park from Samsung.
Hello, my name is John Park from Samsung Electronics. Today my talk is about current status and future prospect of STT-MRAM for mainstream memory. So STT-MRAM is based on the knowledge about magnetization switching bit. So it requires fundamental understanding about magnetics and combines with technology of microelectronics. So it's like a marriage between magnetics and microelectronics. So throughout the development of technology from HDD ready head to toggle MRAM and in-plane STT-MRAM, we have accumulated fundamental understanding about this interesting technology. And Samsung finally has launched the first embedded STT-MRAM product based on the perpendicular MTJ in 2019. So one of the biggest merits of STT-MRAM is to utilize wide spans of MTJ performance. As you can see here, by improving MTJ stack and module process, you can increase the switching efficiency of MTJ bits. So you can transit from cold storage memory type to working memory like a graphical frame buffer. And basic idea is to utilize the perpendicular magnetic anisotropy of MTJ cells, so you can shuffle the critical energy barrier for switching from the conventional consumer type eFlash memory to more advanced industrial and automotive application, and even for the providing solder flow capability, you can increase data retention characteristic. And also you can transit to the working memory, like a graphical buffer memory, which requires a higher speed, but a little bit lower data retention. So you can change the MTJ performance to extend MRAM application. So Samsung is developing MTJ technology with the three-dimensional advance. For example, higher density and higher speed and higher retention. We are exploring technology for the conventional code and data storage, and also MRAM and working memory. One innovative idea that we present in IEDM 2019, we are proposing a single chip hybrid memory, which provides two different levels of MTJ performance. In section 1, we can provide high speed and high endurance memory, and in section 2, we can provide high retention characteristic by simply changing the critical energy barrier for switching from this end to this end. So we can provide just by implementing one photo layer of MTJ module process, we can build STT-MRAM based on-chip hybrid memory. you can hear more in my talk in MRAM forum. Thank you for listening.
Hi, Jeong.
Hello.
Okay, so here I have a question for you from Yajui from National Taiwan University. He's asking from your main presentation, slide 28, the discussion where you discuss about CD versus PMA. And he's asking, can you explain more in details why PMA manipulation is more efficient in tuning retention than CD manipulation?
Yeah, in that slide, I've compared the tunability of MTJ data retention characteristics, and I have changed the MTJ simply by changing MTJ CD, or I have implemented some secret process to tune the magnetic anisotropy of MTJ cells. But simply explaining, actually, if you increase the MTJ CD, that's the energy barrier for switching is the combination, the multiplication of the anisotropy energy per volume times the volume. But if you simply increase the volume, we always have the demagnetizing effect. So it becomes more dominant as we go into infinite size. So you cannot obtain the high data retention as you plan by just simply increasing the CD. So in some specific cases, if you have some big saturation magnetization in your magnetic film, then the impact will not be dominant as you plan. So which means in even smaller size, you can experience higher HK. So effective anisotropy energy will become higher. So with that, if you have some effective process to tune the magnetic anisotropy of your film, that will more dramatically change the energy barrier for switching.
And I guess for the resistance of the device in the both area, it's also important to keep
Right.
compatible with VDD.
Yeah.
So there is a series of questions from Xingji Qiang, which is asking things I guess you will say you cannot say. What is the write speed and retention of EMRAM product released last year?
Yeah, I'm reading the question. I'm not quite sure that we have released the specification of the MRAM product, but as you can find out the information out there, but the first product is mainly about the storage type. So typical operation speed is not very fast. So and the retention. That's the category in the consumer product, so it's not quite a big.
Yeah.
So
Okay.
you can imagine.
So maybe this one you could answer. What is the main difficulty when expanding the EMRAM from eFlash to main memory? Is it endurance, density, or power?
Yeah, that's why I've explained that we are exploring the MTJ stack and module process, all different directions. We see many trade-offs when we optimize the film and process. So you should take care of all details in the interactions between film and process. So if I just say density is actually a biggest problem because you need to optimize both from the film side and the patterning side. There are many challenges in the patterning for the denser MPJ array. It also affects a lot in the MPJ property. So naturally, you need to develop lower resistance MPJ stack for the smaller and denser MPJ array. So you need to have a thorough consideration about the MTJ stack and process together. And also, for the main memory, as Eric previous talk, he presented difficulty of the optimizing MTJ stack not to have any writing failure like ballooning or other distribution problem. So this is also another big challenge. So
Okay.
it's a big project to explore MTI film.
Yeah, I can understand indeed. A question from Mustafa Pinarbasi. Is PMTJ deposited at the same time or separately for the two zones of hybrid versions?
Yeah, that's the most beautiful things. I have deposited just once the same MTJ stack, and we haven't, changed the MTJ stack for different ones.
And I guess you cannot disclose how you are modulating them in Partisan.
Right.
Okay. So then I propose that we end the question session for you. Thanks a lot for your presentation. Looking forward your next product. And now we are going to move to next speaker, who is Johannes Müller from Global Foundries.
Yeah, hello everyone. My name is Johannes Müller. I'm from Global Foundries, and in my presentation, I will be talking about line of defense strategies for embedded STT MRAM, which we are currently implementing as a non-volatile memory solution for our 22FDX platform in Dresden. So this work was in collaboration with KLA, assisting us with the magnetic metrology. So here's the actual problem statement of my talk. So when you think about an MRAM product being manufactured in a foundry, of course, if you have wafer level product sort, you can easily do your wafer disposition and even differentiate between parametric driven yield loss, which could be a single bit write margin driven, for example, and of course defectivity induced yield loss, which are single defect entities that can have some downstream effects on the further processing of the device, leading to some yield loss. The problem is wafer electrical sort is not always the task of the foundry, meaning our wafer dispositions or our judgment of the quality of the material has to be solely based on defect inspection and parametric single device testing. So parametric single device testing can, of course, be done with a parametric tester end of line, utilizing the known hysteresis loops of MRAM, extracting HC for data retention and magnetic immunity safeguarding, the MR for, of course, high temperature read margin safeguarding, and then also the VC will tell you something about your write margin and cycling endurance performance. Defectivity-driven yield loss is like in any other kind of technology, safeguarded by defect inspection tools. So your physically discovered defects have a certain kill rate that transforms into the product yield. And once this correlation is known, there can be a solid judgment of the quality of the material. So what's the actual problem? The problem is that defectivity-driven yield loss can be treated like in any other kind of technology, but the detection of parametric yield loss induced by the MTJ stack or the MTJ patterning at final test is way too late and would put too much material at risk. So a line of defense for this kind of parametric yield loss scenarios is has a high return of invest, since the moment the MRAM is inserted onto the CMOS platform, the wafer has already executed most of its critical masks, meaning it has acquired most of its critical value. So in my talk, I would like to present strategies not only on monitor test loop flows where we go through all the necessary magnetic equipment, but to transfer this kind of MTJ safeguarding directly on product. So I will touch the film level, PMOG, CIBT, and FMR capabilities, as well as the new pattern PMOG technology, which gives us even a post-patterning readout of our MTJ performance. So hope to see you on the conference virtually, and yeah, have fun.
Hi, Johannes. Nice to see you.
Kevin.
Okay, so actually very interesting talk, very unusual, let's say, for this type of presentations, and very interesting. So a lot of new tool development, let's say, or characterization development. Actually, I had just a naive question. typically, how much of what is the percentage of wafers which are defective within a production day, let's say, or month? I don't know how you are scaling it.
Difficult to answer. We're just in the ramp phase. So most of it is debugging of new products. So since Dresden Fab 1 is only ramping up, so there is no, let's say, 1 year experience with a certain defectivity. But at the moment, I say 0 because we have we have all our safeguarding in place, right? So at the moment, like I showed in my talk, setup wafer looping is very important for us. And once we are clean there, then there is no defectivity coming from MTJ stack alone. Other defectivities, like in any other foundry, are still dominating, like coming from other processing steps or integration in general. But MTJ, the position itself is very solid for now. I mean,
For now,
yeah.
Good. And so these defectivities are mostly related to the deposition tool, or can it come from also from the front end of line wafer, or maybe the patterning later?
Well, I think defectivity from MTJ is safeguarded by particle measurements, of course. So there's no clear particles. So when we talk about defectivity coming from MTJ stack, then it's usually thickness deviations. Of course, film depth rates being not on target, and this will lead to other MTJ properties. And I think everyone working with advanced MTJ patterning knows about partial short. This is a typical issue for patterning-driven defects. So if there's anything off, there's usually very soft shunting of the MTJ on the sidewall. So these are the, I would say, typical drifts, if you can see any, would be, sidewall shunting or free layer thickness drifts that are immediately reflected in our device parameters. All the other
particle contamination cannot be.
For us at the moment, not particle contamination. If there's anything wrong with the target, then this is easily picked up by monitoring. So,
actually, a good question from Xing Shixiang. How about electrical yield from patterned MTJ? Any method to detect it, to detect the failure just after the patterning?
Well, at the very last section in my talk, I tried to show something which is a very nice development. I think was also tested at IMEC and in collaboration with KLA is this pattern PMOG. So this is actually very good question because after patterning, most of the thin film methodologies, of course, they don't work anymore. Right? So you need to do this post MTJ deposition. But in the end, what counts is what are our pattern pillars doing. So many MTJ parameters massively change after confining them to a small volume, like in a pillar. As everyone, I guess, know, this has some implications mainly on free layer, but also on the soft performance because, of course, post-patterning, you're talking about a completely different environment from a infinity extended thin film to a very confined system. And there, at the moment, I only see the pattern PMOG, which is luckily capable of picking up enough signal from the already patterned film to give us at least some indications of free layer healthiness. This is, of course,
that's for the magnetic yield, let's say, but regarding the electrical yield from non-electrical measurements, I guess you cannot.
The electrical yield from non-electrical measurements. Yeah, I think that was the question. I mean, the HC of the free layer you can see with pattern PMOG, but you can also see it later electrically, right? But we cannot check electrically because this is usually reserved for end-of-line testing. You cannot, at every intermediate metal layer step, you cannot touch down with a big copper needle on copper pads with a big needle. It scratches. You lose more yield actually than you will be able to safeguard. That's why you need non-invasive techniques when you are still in manufacturing, because the touchdown for end-of-line testing is only really at the final metal level before you go to packaging. So yeah, that's the pattern PMOG. Like I said, it's the only one that's at least known to me that can give us some correlation to electrical results post patterning. Yeah.
Okay. Yeah, I guess the answer.
Or maybe I didn't get the question right. So
No, but I think it's any method to detect that you would have some partial shorts from different methods than using electrical measurements. That would be wonderful. Huh?
You can do a cross section. Some people think they can see something there. Some people don't see anything. So it's very hard to detect this. These partial shorts are super thin. They are like monolayers or a couple of monolayers. So, and you also need to be lucky with your TEM cut that you're cutting in the direction where maybe you have your issue, right? So,
and you cannot have statistics on it for sure.
No,
So
and
just a last question from Jace Shimon. When you describe pre-patterning characterization, do you mean on CMOS or short loop film setup?
No, actually, also
Both,
thanks for the question. So we have setup wafer loops, meaning blanket film, but what the talk is mainly about is that we are transferring all these technologies to directly on product. So this gives us the ability not to only see major excursions that extend over several numbers of wafers. With that 100% testing, we can also detect single event excursions, which will only be relevant for a few product wafers. So we are really testing on product each wafer that later might go to the customer with non-invasive or non-destructive methods. So
good to know. Yeah. Okay, thank you very much, Johannes, for your talk. It was very interesting.
Thanks for inviting me, and I go back to bed.
Maybe close the end of the session. Okay. Have a nice evening or night. Now, next talk will be given by Yuan Chen Li from TSMC.
Hello, everyone. This is Yuan Li from TSMC. It's my honor to be here to represent TSMC MRAM team to talk about our work. The title of my talk is STT MRAM in 16nm FinFET for solder reflow applications. Here is the summary of my talk. First of all, I show you TSMC N22 ULL embedded MRAM status. Currently, N22 embedded MRAM is in mass production. The production wafers are stable and high yield. And we demonstrate embedded MRAM on 16nm FinFET technology node for reflow application. The data retention is 230 degrees C for 20 years on reflow design. It is high and good for automotive applications. We also demonstrate 15 nanosecond write plus with capability on reflow application embedded MRAM, and the read access time smaller than 10 nanoseconds for whole temperature and VDD range. No cell current degradation after 100K endurance cycles. And the wafer yield is high and defect bit error rate is low after process optimization.
Hello everyone, my name is Shinobu Fujita from Kioxia Corporation. Today I'm talking about advanced MRAM-based memory systems for near-future computing application.
Hello, Kevin.
Hi. Hello, Yuan Chen.
Hi.
Thanks for your presentation. So, looking for some questions. So far you are presenting data where you are basically downscaling the technology node.
Yes.
Do you have already a target in mind to go progressively toward lowest technology nodes, or?
I'm sorry. I'm afraid I cannot answer this question due to some companies' regulations. But yes, right now we are working on the N16 MRAM, try to make it production as soon as possible.
And did the 16 nanometer node bring a lot of complexities regarding stack optimization? compared to the 22 nanometer or 28?
No, actually, MTJ Fin is quite close between two nodes because they are the same application for the referral application. But some integration takes some improvement to reduce the defect rate and shrink the size and try to get a good yield on the array level.
Yes. And so now you were mentioning that you are getting close to be ready for production on 16 nanometer node.
Yes, yes, I will say yes, quite closely. Yes, right now we have a couple of customers engaged to adopt TSMC N16 MRAM into their product, especially on the MCU applications.
Okay, that's good to know. So we are going to see more and more MRAM in our products.
Yes, I think so.
Very positive. So there is a question from Xiangqi Chang. The property of eMRAM looks just similar to eFlash. Any significant advantages eMRAM as compared to eFlash?
Okay. Yes, actually, in the TSMC, there is a node embedded flash offer on the N22 and beyond. So that's the reason we try to bring the embedded MRAM to replace the embedded flash for now. And also for the embedded MRAM, in terms of the process and mask either. So the embedded MRAM has a high benefit than embedded flash. As you may know that embedded flash need to have 8 more than 10 mask layers. But for the embedded MRAM, it's only like 8, 2 or 3 mask. So in terms of process, it's much easier for the embedded MRAM.
And in terms of material, is it less expensive also? Or because in MRAM we use quite a lot of expensive materials.
Yes, but compare all the costs, embedded MRAM is still cheaper than the embedded flash process.
Okay, and one question from Weishi Chen. What is the right current requirement for 16 nanometer node MRAM? The writing current requirement.
Okay. Yes, for the N16 embedded MRAM, we are targeting on the embedded flash replacement for the MCU. So the writing current is not critical. So yeah, there's the limit for the embedded current is from the metal reliability side. So, but it's I cannot get that much information here.
Okay, so what is important for a flash replacement is the read refresh rate, or?
Yeah, it's the read performance.
Okay. So if no more question, I suggest to close the discussion.
Okay, sure. Thank you.
Thanks a lot for attending the session and giving your talk.
Thank you.
So next talk will be given by Shinobu Fujita from Kyokusa, formerly Toshiba company.
Hello, everyone. My name is Shinobu Fujita from Kyokusa Corporation. Today, I'm talking about advanced MRAM-based memory systems for near-future computing application. There are various kinds of advanced MRAM for embedded or standalone, like a perpendicular STM-RAM and BCMA and SLT and hybrid one to replace the embedded SRAM or standalone DRAM because they have the highest endurance and fastest write in all of number of time memory. Advanced MRAM devices have 3 kinds of benefits. Number 1, the low power for retaining data. Number 2, persistent memory. And number 3, high-speed data storing. Goal of my talk is analysis of benefits through 3 application case study. Number 1, mobile computing. Number 2, cloud computing. And number 3, IoT edge computing. First application is mobile computing. In this case, we can expect last level cache energy reduction over 90% using perpendicular STT MRAM. And also, we can expect reduction of total processor power up to 90%. The second application is cloud computing. We have proposed persistent memory with MRAM DRAM hybrid architecture for cloud computing. And in this case, data to be saved in persistent memory is like this. In this case, the light frequency is high, but data is not so big compared with the main memory. And also, please note that OS, virtual memory file system, is very, very important to save these persistent memory data effectively. The third application is IoT edge computing. In a conventional one is IoT sensor data come from the disperse and the processor and DRAM and NAND flash, and finally the cloud. But in the DRAM to NAND flash is a bottleneck for the endurance benefit. And in MRAM-based systems, we can expect a CPU performance improvement because the processor directly access the MRAM only, and the cloud computing is used based on advanced MRAM only. As I explained in the 3 application case studied, hybrid systems, embedded MRAM, SRAM, and MRAM DRAM is very effective for low power persistence and performance improvement of CPU, and also new OS software is very important to enhance all of these. Advanced MRAM-based system is only one solution for all data applications because of highest endurance. First, it's write access of all non-volatile memory. Thank you so much for watching my video.
Hello, Shinobu.
Hello, Kevin.
Thanks a lot for this very nice presentation, which is giving a very different view on system level requirements.
Okay.
Actually, there is something that I'm not sure to have understood in your presentation. At some point, you are discussing about system level cache frequencies of operation, and you are mentioning that you have been fabricating STT-MRAM with standard SRAM. Did I understand correctly?
Yes, yes. Yeah, and as you might know, the standard MRAM is not ready, very close in this industry. So, but also Toshiba and also Kioxia even now is trying to develop standard. And embedded MRAM is only now available for various kind of industry. So the first application is very popular, but the second one and the third one is a kind of a fundamental analysis based on simulation only now.
Okay. And so is it something that, okay, just is it something that you are planning to tackle also, the embedded market from Kioxia, or you are only focusing on the standalone memories?
Oh, sorry, I watched the question.
Yeah, that's okay, that's okay. So the question to rephrase is, how do you think the low reading speed of eMRAM, basically 5 nanoseconds, compared to SRAM, basically 1 nanosecond? Could that be the bottleneck of bandwidth?
I don't think so much because the frequency to last level cache is not so frequent, and they are compared with level 1 cache or SRAM in CPU core. So based on our simulation, the disadvantage of latency is just less than 10% or less than 5%. It depends on the software situation, but this is not a bottleneck, I think. The advantage is rather than the latency than the reduction of total power, I think.
Okay. And parallelization, can it mitigate the speed of SRAM?
Yeah, and the power reduction is the most important point.
Okay. And so this latency and refreshment frequencies that you presented, is it measured from experimental processors or is it also only simulations?
You were talking about last level cache?
Yeah.
Yes. Actually, we have fabricated their last level cache based on embedded MRAM, and it's joined to the real CPU. We measured this data, and also we compared with the simulation data.
Okay, so it should bring a lot of attention because that shows the real benefit of using MRAM.
Yeah, I think so.
Okay. So if no more question, I would like to thank you again for your talk. It was very instructive, and I think this type of analysis are extremely important to give a perspective on a new technology.
Thank you.
And have a nice day. So next talk will be given by Jack Gwetch from NUMEM company.
Hello, we're presenting a 24 megabit on a 16 nanometer process with sub 5 nanosecond read access time and MRAM IP core. On the left side, we're showing a read smooth plot done at 85C, showing passing at 4 nanosecond across the full VDD voltage range of 0.72 to 0.88. The architecture is using adaptive trimming for read current levels, self-time delays, reference, and sense apps. In the middle, we're showing write speed down to 15 nanoseconds. Our write algorithm is designed to maximize endurance, and we are also using minimum voltage for that same purpose. The write supports flexible operation and adaptive trimming. On the right side, we're showing the write endurance at 10 to the 9th at 85C. We use an accelerated write endurance process by boosting the VBL voltage and then extrapolating back to the write value. The retention for this device is done on a 10-year 125 process. The device is designed for low power operation, featuring a 0.8 microwatt per megabit standby and a deep sleep less than 0.2 microamps. It is also designed to minimize the area with approximately 0.5 millimeters square per megabyte. That is for the full memory subsystem, including memory controller, the error correction, which is a dual bit, 2-bit correct, 2-bit detect error correction, data I/O repair, and an extensive BIST, as well as the memory interface. It is a scalable design architecture enabling rapid customization of memory density, I/O bus width, aspect ratio, and pipelining. Thank you. Hello, Kevin.
Hello, Jack.
Hi.
So I'm not sure, is it a product that you are presenting, or is it still a vehicle at this stage?
We've been doing tons of test chips and testing that extensively over temperature. So yeah, we've done since the 22 nanometer quite a few variants of this design. This is currently generation 5 that we're presenting. Actually, this one was generation 4, and we have generation 5 now out.
Okay, so there is one question from the chat. Could the 10E9 endurance 10 years at I don't know.
It is all on the test chip. Yeah, I think the question is, are all the things presented on the same test chip? Yes, it is all the endurance, the retention, and the write are all from the same test chip.
And so, why are you limiting your test to 0C? Is it because you are targeting certain type of applications? Or?
No, that's what we've tested so far. We do a lot of testing at -40 to 125. And obviously at -40, the write is more a challenge than the read, and vice versa. But we have a lot of commercial applications, and so this is what we're presenting today.
Yeah, that I understood. And so, okay, are you allowed to say the foundry which is taping out your product?
Yeah, it's basically the same foundry that presented earlier. It's TSMC.
Okay, good.
Yeah. So it's both the 22 nanometer and 16 nanometer RTSMC. As you can see, we've targeted a fairly fast read access time.
Quite impressive indeed, yeah.
And there were questions earlier about is that a limitation versus SRAM? First of all, I think the MRAM here is used more as a high-level cache, so not necessarily need to have the same access speed as an SRAM, but the bandwidth can be increased by widening the bus and also by pipelining. So right now we're doing a design at 500 megahertz.
Okay, and I forgot if you are mentioning, did you compare energy benefits compared to SRAM design?
So yeah, we did. Basically on the right it's higher, so it works well for more asymmetric application, read and write. But on the read it's comparable to SRAM for dynamic and about 20x lower for standby. And of course, there's deep sleep where it's literally nothing, since the memory retains the data, contrary to SRAM. So it does very well for large memory where basically the power is incurred in the word being read, and the standby is very low compared to that.
Okay, good. Well, thanks for presenting your
Thank
product.
you. Okay.
Have a nice day. So next talk will be given by Shunsuke Fukami from
Hi everyone, I'm Shunsuke Fukami of Tohoku University. So in my main presentation, I discussed two kinds of beyond STT-MRAM technologies. Okay. As the STT-MRAM with two-terminal magnetic tunnel junction devices has hit the market, there are several fundamental challenges we have to address, which include increasing the capacity, increasing the operation speed, or opening a new computing paradigm. And in the first part of my presentation, I discussed SOT-MRAM technology, which is promising to enhance the random access frequency beyond 200 megahertz. And in the second half, I discussed probabilistic computing, which is analogous to the quantum computing and has a potential to drastically change the conventional computing paradigm. And as for the scaling, my colleague, Butlin Jinnai, gives an invited talk in CG01, where he showed high-performance MTJ down to 2.3 nanometer. So if you are interested in this technology, please visit his presentation. Okay, and in the SOT-MRAM part, I first give a basic introduction to the physics of the SOT-MRAM, and then show a device technology which is compatible with the 300mm CMOS process. The results I show include 0.35 nanosecond field-free magnetization switching and achieve demonstration of the SOT-MRAM chip, which was fabricated with 55 nanometer CMOS process and 400 degrees Celsius annealing. In the second part, first I describe what's the probabilistic computing, and then show our proof of concept demonstration of the integer factorization using perpendicular stochastic magnetic tunnel junction devices. And after that, I slightly touch on our very recent achievement of the 8 nanosecond random telegraph noise using an in-plane stochastic MTJs. Okay, these are the main points of my presentation, and I'm looking forward to the discussion. Hi.
Hi, Shunsuke.
Yeah, hi.
Thanks a lot for your very nice talk, very didactic and instructive. A lot of very nice work. Yeah.
Thank you.
So looking for some questions first. Actually related to the question of Bernard, which is on your switching probability curves for SOT-MRAM technology integrated on CMOS wafers. I was also quite surprised that you do not present a bit error rate measurement, or at least a bit more statistics than 10 loops measurement. Is there a reason for that?
Actually, so at this moment, we only have the results from 10 times measurement, but yes, in the unpublished results, we perform about 10 to the fourth or fifth times measurement, and we obtained a good reproducibility and high, low write error rate. So I'm very sure that the SOT switching is very promising for the low error rate write operation.
Yeah, I'm sure too. Okay, and so regarding your second part of the talk about probabilistic computing, so I think this is also a very fascinating and interesting area of research. Do you foresee from device level perspective complexities in bringing this to more maturity? Because from what I understood, you are so far trying to limit the offset field contribution to the stochasticity itself, and you are proposing various solutions in the literature. But do you see that technology-wise it might be a real limitation?
Yes, so that's a very good point, and I agree with you. So it's a very important challenge, and I guess we can tackle that issue from the two directions. So one is that we have to reduce the variabilities from the device technology. So we have to pay more efforts to reduce the device technology than the STT-MRAM technologies. And the second point is that we can somehow address that issues from the circuit or system level approach. So I believe that from the circuit technology, there are some solution to accommodate the device variability. So that's a very important challenge of this technology. Okay. So did I answer to your question?
Yeah, you did answer. I mean, there are various points to discuss, of course. But I think time is a bit running for this session. I unfortunately do not see questions coming. So, well, I hope we will have more time in the future to exchange, because I think we have many things to discuss.
Yeah, me too. Yeah.
And I thank you for attending and presenting.
Thank you.
And we are going to move to the last speaker of this session. That is Manu Perumkunil from IMEC.
Hello, I'm Manu Perumkunil. I'm the program manager of the Memory Insight program at IMEC. And this is the summary of the second talk in the special session entitled Beyond STT-MRAM. The talk is entitled On-Chip 3D Caches for Advanced Heterogeneous SoCs. And we are especially going to take a cross-layer look at embedded MRAM solutions for these 3D on-chip caches. Now, I thought that this image was very representative of the talk itself, because we are going to look at 3D stacking from an architecture and design point of view. And we're going to see how good embedded MRAM solutions are for 3D stacked memories. We do this by means of a power, performance, and area analysis. The power and performance analysis throw up very interesting results. There is the conventional case, which is represented by scenario 1, where we actually just look for wire length reduction. There your SCT and SOT, like in the normal scenario, they can give power reduction from leakage energy reduction. But the second case, where you actually try to utilize the density of these embedded MRAM solutions and make the cache capacity larger than that of SRAM, that is what gives eye-popping results. So that enables performance reduction for the entire SoC, even though the STT at a macro level and at a bit cell level might be slower than the SRAM. So these kind of solutions show that architectural innovations and design innovation can be the path to push forward embedded MRAM solutions. The area analysis quantifies how much capacity can be increased for your STT and SoC based caches. We round the talk up with an example hardware demo that shows that this kind of stacking of embedded MRAM solutions is something very feasible. Thank you.
Hi, Manu.
Hey, Kevin.
Thanks for attending this very last talk of this MRAM forum session.
No problem.
I hope you're not too tired.
Yeah, that's okay.
So let's see if we have some questions regarding 3D integration. So do you think it's something that can come as a reality one day, or do you foresee technology complications?
No, it's at least I see it coming in the near future itself, right? 3D integration, stacking for sure. It's about how much, which kind of 3D integration technology they're going to use, right? Which kind of 3D integration schemes they're going to use, and what kind of fine pitches, they're going to go towards. I think you'll see a roadmap very shortly appearing. There will be vertical growth. That horizontal growth is kind of limited. There'll be vertical growth now, and just like you see in HBMs and NAND flash and everything, you kind of see that in the embedded, chips as well.
Yeah,
embedded SoCs.
But this is work that you made for MRAM, but does the same type of analysis exist for other type of non-volatile memories?
Well, embedded MRAMs, so both STT and SOT are relatively more mature, so we did it for that, and we had the data from the hardware demo we did for embedded MRAM, right, from embedded STT. The one where it was, we actually did the wafer to wafer 3D integration with an MRAM on top and and a CMOS wafer, right? So then MRAM plus CMOS and TSV stack on top, just for demonstration. And we saw that functionality was pretty good from your RH loops and your RV loops. So it works. I don't see why it shouldn't work for, if your interconnects are good enough, they're functional enough, it'll work for other non-volatile technologies as well. But the biggest benefit is, of course, the advantage of conventional embedded MRAM solutions, right? You see that they can work still with the power domain for logic, and the density compared to STT and the compared to SRAM, and the performance compared to SRAM. So as long as we have those advantages compared to other embedded solutions, other non-volatile solutions, this will be the first thing people will look at for these kind of stacking and all that. Yeah.
And I actually have a side question to this. So does the wafer bonding imply that you can now process MRAM with different thermal budget and, for example, go for more complex materials which are more performing?
That's a very good point, right? So I have one particular slide in that. Let me just check which slide that was, where I talk about design considerations specifically for 3D, right? So it's slide 12. So if you go to this kind of 3D stacking, not only can you do design and architectural changes to mitigate the other problems, right? Because you have more area on the top to kind of come up with ECC, to have a separate power domain, right? Like you said, to explore different materials there and many other things. So you can independently optimize the memory layer and the SoC chip below. And you can, make it better for MRAM. You don't have to stick to too much logic compatibility there.
That's very, very interesting and promising.
Yeah.
And does the wafer bonding add some thermal budget also, or is it something operating at low temperature?
No, so that's something, yeah, we still need to look at, because cooling solutions with 3D stacking, you'd have to look at, even the kind of stacking, right? Or do you want it below logic for the interface directly to external memory, and do you want it larger so that your logic is on top, and then this usually that requires higher thermal dissipation because it's more active, right? So accordingly, a thermal budget balance and giving more space to that, that's still a lot of experiments that we still have to do.
Okay, then thanks a lot, Manu, for this very, very interesting talk.
No problem.
And
Thank
for
you.
attending.
Yeah, sure.
And with this, I'm going to thank all speakers once more for providing all these very nice and interesting talks, and to the audience for attending to this 12th MRAM forum. And with this, I'm going to close this session.